Hi, so this is the second Alum post lab video. As you can see from the picture that I imported in this video because I didn't want to disturb the bottle, there hasn't been any additional crystal growth. Some potential conflicts could be that the temperature in my room has varied considerably, and especially since it's been winter, I've kept my room at about 80 degrees Fahrenheit, which could be a temperature that the crystals are soluble at. In addition, since there's not much sunlight, the evaporation process is exceptionally slow, and since the crystals grow when the liquid evaporates, this could also hinder the growth considering the outdoor temperature. Furthermore, the Kim wipe could be hindering the evaporation as the liquid may be evaporating more slowly with the presence of the Kim wipe on top. So, based off the amount of aluminum that we started with, we calculated the theoretical yield and then our experimental yield, and then we're eventually calculated the percent yield. The first step was finding the moles of aluminum. So we weighed the initial mass of aluminum, which was 1.0128 grams, and then using the molar mass of 26.98 grams, we found that there were 0.0375 moles of aluminum. And then the second step was converting the moles of aluminum to moles of alum. And we do this by looking at the overall stoichiometry of the equation and using that factor to convert the two together. However, the equations that were given to us or that we deduced were in 4 separate steps, as you can see from the picture below. So what I did was combine the 4 steps into one overall reaction, which, as you can see, is 2 moles of aluminum solid plus 2 moles of KOH aqueous plus 22 H2O liquid plus 4 H2SO4 aqueous yields 2 KAlSO4 plus 12 H2O solid plus 3 H2. And as you can see, there's a 2:2 mole ratio, which simplifies to a 1:1 mole ratio between aluminum and alum. So for every 0.0375 moles of aluminum, there's also 0.0375 moles of alum. The third step was to convert the moles of alum to grams of alum using the molar mass of 474.39 grams, which led to 17.81 grams of alum, which was the overall theoretical yield of the experiment. So to calculate the percent yield, it's the actual yield over the theoretical times 100. The actual yield was measured by measuring the mass of a beaker and then measuring the mass of the beaker with the additional precipitate at the end, and we found it to be 12.723 grams. And to find the percent yield, we did 12.723 grams over 17.81 grams times 100, which was 71.45%. So clearly our experimental yield wasn't 100%, which could have been for a variety of reasons. Firstly, we started off with the assumption that the initial mass of the aluminum was totally pure, the 1.01 grams. However, that was definitely could not have been the case as it was mixed with other impurities, so it would have been less than the additional mass of aluminum used in the first place. In addition, in reaction 1, when we dissolved the aluminum into KOH, it's possible that not all of the aluminum was properly dissolved, and then during the filtration we filtered out some of the actual aluminum that could have contributed to the final alum. In addition, during the precipitation of the solution, the entire solution actually froze in the first 10 minutes, and we then waited for it to defrost back at room temperature and after decided to isolate the solid. However, because we only let it freeze for 10 minutes and then left it back at room temperature, it's also possible that not all of the alum precipitated and instead dissolved back into the solution, since it is soluble at room temperature. Other smaller errors could have included not rinsing the cup the entire way or properly with the ethanol solution, which left some of the alum stuck to the sides. In addition, when the acid was added, some of the solution splashed onto the sides of the beaker instead of mixing with the solution, which also could have led to a decrease in the final product. Hopefully in the next few weeks we'll see additional growth.